Go to cloud. I hope it's going to work because I switched things. And screen share. Share. You see my screen?
Not yet.
Yeah, looks good.
Now we do.
Now we do.
And this is class number 13, I think, no? Okay, so hopefully we're going to have some fun today. We're talking about the photons, really. So it's more general. It's a Maxwell's equation, the photon, the Klein-Gordon, and the Proctor equations. Now I will post some of my lecture notes online later on today. And since my deadlines are over, I'll start also grading your homework. So let's do a quick recap. So right now we're talking about photon, and I think time to much beyond photons today. So, right, so last time what we spoke about very briefly, we spoke about units. So in particle physics, the units that are most common in use are the Heaviside Lorentz units. Then we spoke about Maxwell's equations. Right, so classically, everything we did so far was just classical, like Maxwell's equation, Gauss' law, and then Faraday's law. And then Gauss' law for magnetization, and Ampere's law. All units are CR1. And then I said that we can write this in a more compact form by introducing the Faraday tensor. Which is the anti-symmetric tensor. So it has to have zeros on the diagonal, and then minus E1, minus E2, minus E3, E1, E2, E3, and then minus B3, B2, and minus B1, and of course the opposite, B3, minus B2, and B1. 1, 2, 3, of course, are X, Y, and Z. It is a tensor in the sense that under a Lorentz transformation, it transforms like a tensor. Or in other words, you can think of it as a mapping from two covariant vectors to R. More on that in the GR course. Now, if we, so introducing this tensor, and now we can introduce also the 4 current. So another 4 vector is the 4 current. Just the density rho or C rho and the current J. This will denote by J mu. So this is a 4 vector. Again, it transforms like a 4 vector. Then the non-homogeneous Maxwell's equations, right? I can write them down simply as d mu f mu nu equal J nu. Very simple, very compact, very elegant. Simply plug in. Remember, what we really have here is a sum over mu. If you choose nu equal to 0, then we have d0 f0 0, this is 0, plus d1 f1 0, so dt e1 dx e1 plus d2 f2 0, etc. So this is just nabla.e, which is equal to rho. And this is for the 2 of the Maxwell's equations. If you want the other 2 Maxwell's equations, then the easiest is to introduce the potential. So you have seen potentials in classical E&M. So you have seen the vector potential and the scalar potential. So the vector potential in classical E&M the vector potential came out from the mathematical identity. You can always write down B equal nabla cross A. And since the divergence of a curl is always 0, then for any vector A, this automatically fulfills the Gauss law for magnetization, right? This equation here. And then there was an introduction of the scalar potential phi, because we could always write down E plus dTA is some gradient of phi. So we had two potentials, scalar and vectorial. They don't play a role directly because we don't measure these potentials, we just measure the fields. But as you're going to see in quantum mechanics, this is going to change. We actually do have effects that depend on the potential, such as the Aharonov-Bohm effect. And we introduced the 4-vector potential. A mu as phi in the zeros, and then a vector A, the 3 components. And again, this is a 4-vector. And then the 2 homogeneous Maxwell's equations. I can write it down as F mu nu equal d mu a nu minus d mu a nu. Again, nice, elegant, symmetric, very nice. Contains the same information that that is in the original Maxwell's equation. Only the relativistic invariance here is very clearly manifested. It's very clear that all the symmetries that happens here. Now we can use the 4-vector potential to write down the inhomogeneous Maxwell's equations, right? This equation here. If I just plug it in, then the definition of F mu nu from the second of Maxwell's equation, then we write it down as d mu a nu minus d mu a mu is equal j nu, right? I just use both of them to write down this equation. Now this operator, d mu, just dt squared. If you're confused, there's 1 over c squared here, minus the Laplacian is denoted with a square, and the name is called the D'Alembertian, after D'Alembert. This is the 4-dimensional Minkowski space analog to the Laplacian. So using this notation, we can write down the this combined equation as the D'Alembertian of a nu minus d mu a mu equal j nu. Very compact form. It's very confusing if it's the first or one of the first times you see it, but it's very handy to work with mathematically. It's very easy to do it numerically, right? You just tell the computer what to do, and the relativistic aspects of the problem of classical ENM is immediately manifested using that. Okay. The problem is that, as I stated, the choice of the scalar potential phi and the vector potential A is not unique. There can be several choices which we can use, and they will give us the same physical results, because physically, at the end of the day, we're measuring the fields, the electric field and the magnetic field. Okay, so the way out, what we call it, we said that there is gauge symmetry or gauge invariance. We're going to gauge it out. But before I'm going to do that, I want to stop and see if you have actually, because now into somewhat more technical things, which presumably most of it you've seen. I'm not sure that all of it, but if not, this is a time to stop before we get into more deeper and more, somewhat more technical issues that I'm sure you haven't seen. So any questions right now? It is one of those things that there is some chance that you might lose me. So I want to avoid that in advance. It's usual, after you do it long enough, then it gets kind of, I wouldn't say automatic, but you see immediately why it needs to be like that. But if it's one of the first times you see that, then it can be quite confusing. So I'm taking into account the fact that some of you might be confused. But it's the end of the day, it's your responsibility if there is something that confuses you to come and ask. No questions? Okay, in that case, let's go on, proceed straight away. So the this potential formalism, as I said, is that phi and a, the vector a, or the 4 vector a mu, they are not uniquely determined. Now, and of course, the reason is that we do not measure the potentials, we only measure the fields, and the fields are derived from the potentials. So we can add to the potential a gradient of any arbitrarily scalar function, which will not affect the resulting field. This is known as a gauge transformation or gauge choice. So gauge transformation. With adding to the potential a gradient of any arbitrary scalar function lambda will not affect the resulting fields. Which is what we measure. Right, so if I choose a mu goes to a prime mu, which is just a mu plus some gradient of a scalar field, lambda, lambda is any scalar function of space and time, right? Just to make sure, right? For example, the temperature is a scalar function, means it gets a scalar value, but it's defined anywhere in space, right? I mean, everywhere I can put a thermometer and measure the temperature and I get a scalar result, but it's defined anywhere in space, right? So this is the meaning of a scalar function. Electric field is a vector function. That means at every point I can take a probe and measure the electric field and I'll get some vectorial quantity. Just to make sure that you're all with me when I say a scalar function. Now, such a transformation is going to leave the electromagnetic tensor unchanged, right? Because remember the electromagnetic tensor F mu nu is just d mu a nu minus d nu a mu, but d mu a prime nu minus d nu a prime mu, right? This d nu of lambda would just give you 0. So this is just going to be d mu a nu minus d mu a mu. And that follows from the fact that the derivatives are commutative, right? So since d nu lambda is equal to d nu lambda, right? So fields are unchanged, or the Faraday tensor. Hasn't changed. Now, making such a transformation, this is known as a gauge transformation. Apparently, the term was coined by Hermann Weyl, one of the founders of quantum mechanics, because it changes the scale of the instrument in which we measure the potential. Now, the symmetry of the fields under gauge transformation is known as gauge symmetry or gauge invariance. Right? So these are just the technical terms that I'm sure you've heard of, just to make sure that we all have seen it at least once. So the symmetry of the field is known as gauge invariance. Or symmetry. Now, when you think of it, given that there is this gauge symmetry, there are two options, right? So option number one is to continue to use a mu, although we are aware of the fact that it's not completely defined, right? So this description is known as spurious degrees of freedom. So we have two options, right? Option one, continue to use a mu. This is known as the spurious degrees of freedom approach. The second alternative is to impose the extra constraint and work only with the physical degrees of freedom. So of course, the disadvantage of doing that is that we're losing the Lorentz invariance, right? Once we impose this extra constraint, then the equations we get are no longer Lorentz invariant, so we can, this is something which is manifested and continue to be manifested in the way we write the equations. So we might lose track of that. Of course, which choice we're going to choose depends on what we try to. Right? Both approaches have their advantages. Here we are going to study the physical degrees of freedom, so we choose the second approach. So this is the approach we choose.
Asaf, can I ask a quick question from a few minutes ago?
Yeah.
So I'm wondering about the, it's kind of a detail, but you put the prime on the A this time and not on the index. Yeah, I remember a few weeks ago it was the other way around. Is there something crucial going on here?
I know. I haven't had time to think of it. You're right. The reason is that this is taken from a different textbook. So I had to think a little bit because it's a mu or a prime or a prime, because I'm sticking, a mu is, let's say mu is equal to 2, right? It's still the second component of the new vector A, right? It's the y component of A.
Right.
It's the same vector A mu, but now it's a second. So it's the same component, but now it's a different vector. I'm not sure that I'm fully consistent with myself. I have to have a look at that, and simply I did not have time to think of it all the way through, so I just took it from the textbook as it was. Fully agree. Thanks for the comment. I was wondering about that myself, and I just said, look, I don't have time now to think of it carefully, so I just follow the textbook. Okay. Well done for pointing out, for seeing that.
Asaf?
Yes.
Can't we impose a constraint that is by itself Lorentz invariant?
Well, the system is still Lorentz invariant, but you don't see it right away from the equations once you impose this extra constraint.
Okay, I guess I'll see.
You'll see it. I mean, everything is still Lorentz, but you just don't see it right away. Okay, let's see that. So, yeah.
But if it doesn't affect the field, then this constraint, is it only just for comfort and for just approaching it in a different way, or does it have actually an effect on the field in the end? Because you said that adding the scalar field does not change the electric magnetic fields.
It's not going to change the electric field, that's true, but this is in the classical. This is the classical approach. What we do right now is just the classical, right? We haven't quantized anything. In 5 minutes, we're going to start quantizing things, right? And then I'm going to show you that this is going to be useful in determining the properties of the quantized electric field, which is, we're going to call it the photon. Okay, so classically, it's meaningless. You're right. Well, it's not meaningless. It's just, sorry, it's not meaningless. It's a mathematical game. Quantum mechanically, this game has a meaning. Okay.
Yeah, thank you.
All right. This is... Okay, so we're going to use the gauge symmetry to get rid of one of the degrees of freedom. Of course, we have various ways of choosing lambda. So we will choose lambda. We will choose lambda such that d mu a mu is equal to 0. Okay, so we have this equation here, right? We're going to choose lambda such as to get rid of this term, of the second term. And so we're going to choose lambda to be such that d mu a mu is equal to 0. And such a choice of lambda has a name. This is called the Lorentz condition. In fact, as I'm going to show you in a few minutes, there is more than a single choice of lambda that will fulfill the Lorentz condition, right? So with this choice of lambda, right, the two inhomogeneous Maxwell equations they become D'Alembertian of A mu is equal J mu, or A nu. How did I use? I use okay, well, I just plug it in here. I use here nu. So not that it really matters, just to be consistent with myself. The Lambertian of A nu is equal to J nu. Okay. Remember, J nu are the currents. So if we have no currents, if we are in vacuum, right? So in vacuum, What do we have in vacuum? We have a free photon, right? So in vacuum, we have a free particle, free photon. It's not a photon yet, it just feels. Free photon. Then the equation becomes the Lambertian of A nu is equal to 0. Now, why do I call it a photon? What is this equation really describing, right? Remember, what is the Lambertian? The Lambertian is what? The Lambertian is dt squared minus nabla squared, right? So what does this equation tell us? That A nu, right, the 4-vector potential. Well, what does it satisfy? What equation do you see here?
Wave equation.
Exactly, right? This is a wave equation, right? This dt squared minus nabla square of A, right? It's a wave equation. And what is the velocity, the phase velocity? What is the phase velocity of this wave?
One.
Exactly. It satisfies a wave equation with the speed 1. What is the speed 1 in real units? This is natural units, right? So what is it in real units?
C.
C, exactly. This is speed of light. Right? So I knew this 4-vector potential, right? I can think of it, this is a vector that satisfies the wave equation, which in vacuum travels at the speed of light. Okay, now I did not quantize anything, right? This is just, everything is classical. But just that you see what happens here, right? So I played with the mass and then I got something which looks quite familiar. Okay, maybe not familiar at first sight, but afterward it becomes familiar. Okay. Okay. Now let's quantize. Questions? Okay, so now let's quantum interpretation. Not really quantizing because this is not a course in quantum mechanics, but I'm do a quantum interpretation. A quantum interpretation to the electromagnetic description. Okay. So everything we did so far is completely classical, right? But we know that photons are quantum objects. So we need to quantize them. So what I'm going to do, I'm going to start thinking of A nu as a wave function of a quantum photon. And then I'm going to have a new interpretation to this equation. Now, why am I going? What motivates me to think like that? Why am I doing that? Why am I doing that? So remember, all of you have learned quantum mechanics, right? Is there anybody who did not learn quantum mechanics? No, so I assume you all have, right? So in quantum mechanics, right? How do we quantize a classical system? What is the quickest approach? I would call it quick and dirty because it doesn't contain too much of an insight, but it tells you what to do. So how do you quantize a classical system, right? Question you. Classical system, I want to quantize it. What would I do? Just thought you all said you learned quantum mechanics. Let's say I have a free particle. I want to quantize it. I want to treat it as a quantum mechanical object. What do I do? Yeah.
For a free particle, we just postulate the quantum momentum.
What do you do with the momentum?
You postulate that it's fixed.
No.
As it comes in a quantum.
No, I do something else. What do I do with the momentum? I don't postulate. I postulate, yes, but I don't. What do I postulate? Come on, you're not too far. I think the momentum, and what do I do with that?
You say that it's a complete multiplication of h bar, usually.
Yeah. What do I do with the momentum? What does it become in quantum mechanics?
An operator.
An operator, right? I promote it. I take the energy and the momentum and I promote both of them into operators. Right? So I take, we promote the energy and momentum into operators. Now, just out of curiosity, what is an operator? General, what is an operator?
Something that acts on a vector.
And acts and do what?
And returns a vector.
Good. Doesn't have to be a vector, it has to be a function. What is a function? I just want to make sure that you're all with me. What is a function?
Vector in the right vector space.
No, a function for me, a function is a box. Okay, I'm surprised how much this thing not often discussed properly. Well, a function for me is a box. This is a function. What? What enters the box? Function. What enters the box?
A value?
A number. What gets out of the box?
Another value, another number?
Another number. Right? So sine of x, I put the value x, I get the value of sine of x. That's a function. What is an operator?
The same only with vectors?
It's a box. It's a function. It can be a wave function. You can treat it as an operator in Hilbert space. That's okay. That is an operator. Okay. I get a psi. That can be h psi gets out. But this is another function. Okay. It's Hamiltonian. That's all to it. I try to make a little bit of order in your brain, in case you need it, in case you're confused. Okay. So.
Can this be continued? Is there something that takes an operator and gives back an operator, or does this kind of end here?
Yeah, it's a functional. No, sorry, functional takes a function and gets a number. I need a minute to think of that before I give you a proper answer.
No, it is. You can think of conjugation as something like that. It takes an operator and it turns another operator.
I guess you can do that as
Okay,
well.
right. Okay.
Okay.
Thanks.
I think when you think of it like that, things get much simpler. It saves you a lot of confusion when you do quantum mechanics in general. Okay, that's my approach. So we say an operator operates on something, right? So it operates on a wave function, right? So these operators act on a wave function. Psi. Okay, of course, h bar is equal to 1. I just put the h bar just to make sure that not to confuse you more than needed. Okay, so one way to derive, it's not really derivation, I told you, it's just a quick and dirty interpretation, right, is I can just simply start with the classical energy momentum relation, right? So if we start with the classical relation, it says that E is equal to the kinetic energy plus the potential energy. Right, and then we apply the quantum prescription. So quantize, right? That means that these two sides become operators that act now on wave functions. Then this one gives us minus h bar squared over 2m number squared plus v psi equal I h bar dt psi. And voila, we got Schrodinger's equation without the need to do anything. Okay, of course, this is true for non-relativistic particles. Right? Schrodinger's equation is true only for non-relativistic particles. Simply states that the total energy is equal to the kinetic energy plus potential energy. Right. Now let's do the same for photons. Let's do the same trick for photons. I told you I'm cutting down like crazy. It takes 3 lectures in quantum field theory to get it done properly, but I'm just cutting it down. That you can see it down. So being massless, what do we know about the photons? That are massless, right? So being massless, right? Then we have for the photons that E squared minus P squared is equal to 0, right? This we know for them being massless particles. I forget about the C here. Right? Now, if you write it in covariant form, what would be a covariant form of writing that? This equation. How do you write down E squared minus P squared equal to 0 in a covariant form?
P mu, P nu?
Of course. Right? That's true for a photon. Now we can write the energy and momentum operators in covariant notation, right? So it's pretty much straightforward, right? Because if we know that P mu is E P, right? So in quantum mechanics, so again, quantize. right? So what do we get? I dt and minus nabla. So I d over dx0, d over dx. I want just have to be careful here about the signs, because this is just I d mu. It's an upper index. Okay, just with the sign, because we have a minus delta, so it's d mu. It's an upper index. And of course, p mu is just E minus P. So it's just I dt and nabla. So this is just I d mu. So overall, that what we get is that when we promote the photon momentum into an operator, right? Then we get that p mu when it's promoted to minus d mu, which is minus the D'Alembertian. So we get the following interpretation for the classical equation, right? So this allows the quantum mechanical interpretation to the classical equation, D'Alembertian of A mu is equal to 0, which we just write down, right? So in QED, the 4 potential A mu becomes what? Again, it's an interpretation. What does it get?
An operator, or a group of operators.
No, A mu is not the operator. The Lambertian is the operator, right? The momentum turns into operator. What is A mu? If it's an operator, then it operates on what?
A vector or a function?
On the wave function, right? So A mu, right? So in QED, the potential A mu becomes, so it's done in red, right? The wave function of the photon. Right, you already seen that it travels at the speed of light in vacuum. So the classical equation, right? The Lambertian of A mu equal to 0. Remember, it's a classical one. It's a 4-dimension, but it's a classical. I did not quantize anything. Now I quantize, right? This is a classical. So the classical equation the Lambertian of A mu equal to 0 is now to be interpreted as a quantum equation. It is now interpreted as a quantum equation that describes the kinematics of a massless particle. Right? P mu equal to 0. This is exactly what we expect to see from a photon. So it is a quantum mechanical interpretation. Questions? Any questions? Anybody?
In quantum mechanics 1, we use fields as classical objects, which act on the quantum objects we call, say, electrons.
Right.
And extract results like the Zeeman effect and Stark effect, and even the hydrogen atom, which uses the electric field.
Mm-hmm. Yeah.
How does it? Okay, let me ask this like that. In what limit do we get this behavior? What limit of this general theory?
Well, okay. The limit would be non-relativistic limit. Remember, we had this small table at the beginning, and I said that when things are relativistic and small, then we live in the world of quantum field theory. What I'm showing here is a quantum field theory treatment. Right? In the quantum field theory, each field is associated with a particle. Well, the particle is associated with an excitation of a field. Right? Its excitation of a field gives you a particle. And remember what I said, that if you are in the limit that things are non-relativistic, then of course quantum field theory reduces back to quantum mechanics. Okay?
So in the limit of low velocities and low energies, the behavior of the description is exact, and when the energies are too high or the velocities are close to the speed of light, then you have to get the more general field theoretical framework.
Essentially, yes. Essentially, yes. Remember when we said, I kind of said that. I didn't really.
Yes,
I said that when you have examples of according to the quantum field theory prescription, the Feynman diagrams that we draw of interactions between particles, right? Particles only interact with each other by exchange of these virtual particles. In the limit of low energies, then they exchange many particles, and all of them have lower energies, and then we see these as fields. Right, this is what we see what you just described, right? The Born approximation, or any scattering experiment that we're seeing, that we argue that the field is, that the particle is being affected, let's say E&M, it's affected by the electric field of another particle, the charge. Right? But when we speak of very high velocities, then or cases in which we have exchange of a few particles, such as the photoelectric effect, then there is a single emission of a photon, for example, or that there is an exchange of individual but very energetic particles, then no longer treat the concept of classical concepts. Then the treatment is fully in the framework of quantum field theory. Again, I kind of mentioned that at the beginning. Quantum field theory was born by the need to merge quantum mechanics with special relativity. Quantum mechanics works excellent, right? In the limit that nothing is relativistic. But in this limit, you cannot produce new particles, which we're seeing are being produced. Particles cannot, Schrodinger's equation does not allow the production of new particles, right? And we do see this happen. But the quantum field theory treatment does allow decay of a particle into other particles, and does allow production of new particles when two particles collide. Okay?
Yes.
Okay. More questions? Okay, so this was in vacuum, right? What happens, remember when we started with the equation, the non-homogeneous Maxwell's equation, in the Lorentz condition, not in vacuum. So what's the title? It's a small title, right? Photons and Feynman diagrams. Kind of connected to what you just asked. Feynman diagrams. Right, so not in vacuum, but we have the Lambertian of A mu is equal to J mu, right? Not in vacuum. So, this is we derive it classically, right? But now we said that we can have a quantum mechanical interpretation of this equation, right? So what will be the quantum interpretation? Quantum interpretation, right? What is this equation telling us, right? So on the left-hand side, we interpret that as a momentum exchange, right? The momentum change of a photon, right? A mu represents the wave function of the photon, right? And the Lambertian is the P mu, right? Is the momentum of the photon, right? The same way as we have the momentum term in the Schrodinger's equation, right? The exchange of a photon, right? So here, this is the change of momentum of a photon, right? Not just a change of momentum, it's change of energy as well, right? Change of energy momentum, it's not just momentum. So in other words, we can say that the photon is being produced or being destroyed. What produces or destroyed photons? What produces?
Action of particles?
Action of particles, right? So this means, and what do we have here? What is J mu?
Current, it's a movement of particles.
Current, right? It's a current. So what is a current? It's a moving electric charge, right? So this is electric current that emerges from the motion of charged particles, right? Electrons and positrons, right? So how do we describe that? I mean, we visualize that by the Feynman diagrams, right? So gamma right? Or right? So the quantum field theory interpretation of this equation is exactly these Feynman diagrams. Creation or destruction of or change of momentum of a photon is associated or can happen only when we have currents involved.
You say current, but you include just density in that, right?
Yeah, because yes. Again, now it becomes
it's for current.
Yeah, it's a for current here, really. Right. Okay, we're gonna solve that. That's the next thing we're gonna do. Yeah, okay. So let's look at I argue that the A mu is a 4 vector. So let's look at the transformation law. Of the photon. right? So I argue that A mu represents a wave function of the photon, which means that the photon is a vectorial particle, right? Or simply we say it's a vector. So A mu represents the wave function of the photon. It means that the photon is a vectorial particle. So mathematically, that means that under a Lorentz transformation, it will transform like a vector, right? And a term that you might have heard and you're seeing in the literature is says that the photon is a four-dimensional representation of a Lorentz transformation. Dimensional. Of Lorentz transformation. That all it says is that the photon, the components of the photon for vector transform as a vector. Meaning that if we have two observers and both of them are looking at the photon, one is moving with respect to the other, then each one will give you the description that is according to the description of a vector. Now, this is a different description than the description of a scalar function, right? I gave you the example of a temperature, right? I can measure a temperature, it's a scalar function, right? And this is different than equation of the form the Lambertian of phi equal to 0, where phi is a scalar. Massless here, right? There's no mass term here. Scalar function or scalar particle. That means that the wave function phi is invariant under Lorentz transformation. This is not the case for the photon. Okay, so the photon is not invariant. Two different observers will describe the photon in different ways. Of course, these are related by Lorentz transformation. Okay. Now let's emphasize on that. So let me describe the plane wave solutions and the photon polarization. So we saw that the photon, or the four vector A mu, which represents the photon, obeys a wave equation, right? A mu obeys wave equation in vacuum. So we know that the solution to this equation has to be some superposition of plane waves. Okay, so the solution to this equation is a superposition of plane waves. Right, so I can write down, can search for a solution, which will look like A mu is some constant, and then epsilon mu of P, and then plane wave, E minus I P nu X mu. So A is a normalization. That carries the dimension. Okay. P nu is the photon form momentum. Of course, when we use this in equation, in the wave equation, then automatically we get the P nu equal to 0. Right? Which ensures that the photon is massless. Right? So P nu right? You all see that? The vector epsilon mu of the P, this is known as the photon polarization vector. And as we're going to see shortly, this is related to the photon spin. And of course, to the well-known fact that light is polarized. So if we take this solution, right, and use it in here, what do we get? The Lambertian is just d alpha a mu. So d alpha a mu, right, is just minus I p nu delta nu alpha. And then d alpha a epsilon mu is I p nu x nu. And just minus I p alpha minus I p alpha a epsilon mu minus I p nu x nu, which we say is equal to 0 from the star equation. So immediately we see that P mu, P alpha, doesn't matter, P nu equal to 0. Right, I say it doesn't matter. Why does it matter? Because when I have an upper index and a lower index, these are dummy indices, and exactly which index it doesn't matter. Right, I have a nu above and a nu below, like I have an alpha above and an alpha below. So I just sum over them. Okay, that's quite good. Now let's try this solution. We ended up that photon is indeed massless. Photon is massless. Now we use the solution in the Lorentz condition. Use the solution in the Lorentz condition. Right? Remember, we said the Lorentz condition, that was just d mu a mu equal to 0. Right? But d mu a mu is just, right, p mu epsilon mu times all sorts of things which we don't care because it's equal to 0 anyway. So what does this tell us?
That polarization is orthogonal to the momentum.
Exactly, perpendicular to the momentum. So it means that the polarization vector, polarization of the photon, or the 4-vector polarization, is perpendicular to the momentum. 4-vector. So that automatically tells us that we only have 3 components of the polarization vector that are independent, right? Because the 4th one is set by this Lorentz condition. So only 3 of the components effects on mu are independent. But apparently, that's not the end of it. Because even, I kind of mentioned that, right? That even after we impose the Lorentz condition, we still have a freedom to make one more gauge transformation. And because there is more than a single lambda that fulfills the Lorentz condition. Okay? So even after imposing the Lorentz condition, we still have a freedom. We can still make one more gauge transformation. So, remember that the Lorentz gauge, right, just here, right? So d mu a mu equal to 0. So any choice of lambda, right, the gauge that satisfies, or any choice of lambda that satisfies d mu lambda, which is, of course, there's a Lambertian of lambda equal to 0, automatically satisfies the Lorentz condition, right? As I said, there is more than one such choice. So let us consider some choice of lambda. Let's say lambda of x, right? It's a scalar function, right? So it's just I b e minus I p nu x nu, right? It's a, again, superposition of plane waves. B is some constant. So B is some constant. And of course, p nu satisfies the condition p nu equal to 0 for a massless particle. That's a necessary condition. And of course, this gives us the Lambertian of lambda is just minus p squared of lambda, which is just 0. So for this choice of lambda, right, a mu goes to a prime mu. I just lowered the index just to avoid confusion here. This will just be a mu plus d mu lambda. So we said that this is just epsilon mu e minus I p mu x nu. I avoid the a here, right? There's an a, but I just skip the normalization because I already have one normalization. I don't need more than that. Plus I b d mu e minus I p mu x nu. So just epsilon mu e minus I p mu x nu plus I b minus I p mu e minus I p mu x nu. Just epsilon mu plus b p mu e minus I p mu x nu. In other words, since the gauge transformation we said does not change the fields at all, right? That means that the electromagnetic field that is produced by these photons, right, is unchanged when the polarization vector changes like that, right? So the electromagnetic fields are unchanged when the polarization vector changes by epsilon mu goes to epsilon mu prime, which is epsilon mu plus some constant in the direction of p mu, right? That's of course because the gauge transformation does not change the measurable physical properties. Do not change the measurable physical properties. Okay, so we can add to the polarization vector any multiplicity of the four momentum of the photon, and they would still correspond to the same physical photon. Okay, say it again in words. Any polarization vector or vectors that differ by a multiplicity of the four momentum of the photon correspond to the same physical photon. Is what it means. So we do have this extra freedom, which still fulfills the Lorentz condition, and one such choice is called the Coulomb gauge, or the transverse gauge. One such choice is what's known as the Coulomb gauge. The transverse gauge. Right. So we choose B such that the time-like component, so the zeroth component of the polarization is 0. Right. Choose B such that the zeroth component of epsilon mu is 0. Right? So B is simply minus epsilon 0 over P0. That's known as the Coulomb gauge, or transverse gauge. That, of course, automatically leads to A0 being 0. Sorry, because epsilon 0 is 0. Then A0 is 0. Now, if we put this in the Lorentz condition, right? Remember, P dot epsilon is equal to 0. That automatically means that P dot epsilon, but now it's the 3 vectors are 0, which automatically satisfies that nabla dot A is 0. So the divergence of A is 0. So we end up that in the Coulomb gauge, right, the polarization of the photon is transverse to its direction of motion. So how many polarization states do we have? 2, right? This reduces automatically another degree of freedom. So you only have polarization state. You have photon. Photon has only 2 polarization states independently. Well, you know that already, right? Now we're actually showing it mathematically. That also means, actually coming from here, that the 4 vector A nu has only 2 degrees of freedom, which means there are only 2 independent functions that describe the physics. Right? What are these 2 degrees of freedom? This will be the 2 polarization states. Polarization state. Let me repeat again what we did here, because your quietness at this point tells me that you are not that much following necessarily everything I'm saying. We started by arguing that A mu, right, the 4-vector potential, is promoted to be the wave function that describes a photon. And that the equation here with a star, the Lambertian of A mu equal to 0, it's a wave function, right, that describes a photon, right, in vacuum. And then I argued that the solution of this equation needs to superposition plane waves, right? This is the superposition, what is written here and put in a box here, right? Now this superposition of plane waves, right? We have some vector, that's the polarization vector times the plane waves, right? And then I argue that now when we plug in the Lorentz condition, of course, the 4-vector has 4 degrees of freedom, right? You can choose any basis that you want, but the Lorentz condition reduces 1 degree of freedom, which leaves us with 3 degrees of freedom, because the polarization vector needs to be perpendicular to the momentum, right? But I said that this is not enough because I can still choose various values of lambda that would still fulfill the Lorentz condition. So I choose now, right, one which is known as the Coulomb gauge or the transverse gauge, which essentially, this is the choice of the Coulomb gauge, that the 0 component of this polarization vector is 0. And that reduces another degree of freedom, right? And this other degree of freedom, this essentially that tells us that P dot epsilon needs to be 0 or that nabla dot A is 0, divergence of A is 0. Which means that the Coulomb gauge, the polarization of the photon has to be transverse to the direction of motion, right? That's true for photons, that's true for electromagnetic fields, not surprisingly at all, because they're made of photons. So if we look at the photon that travels in the z direction, so for a photon that travels in the z direction, right? Then all the solutions, we can write them down as a linear superposition of the 2 polarized states, right? All solutions can be written as a superposition of the 2 polarized states at epsilon 1 and epsilon 2. Of course, it's not a unique choice, right? It's just a choice of basis. Yeah, question.
When you say all solutions, you mean that all the electrical and magnetic fields can be seen as a result of potential that is some of these?
Essentially,
right?
yes. Yeah.
Because there are other solutions to the equations for A that are not superposition of this.
True. No, right? They're all independent solutions, right? Everything else is going to be dependent. Now, when you treat classically, then yes, you're right. But right now we're looking at the photon as a quantum mechanical entity. Right now I quantized, and that's what I end up with. A photon is a 4-vector, which has a polarization, and the polarization has only 2 independent states.
So I think you're losing out of all of the electrostatic and magnetostatic, all the static solutions, right? These are only wave solutions.
These are plane wave solutions, right? This describes photons.
Right. So the classic thing you're leaving out also is all the static solutions.
Again, in the framework of quantum field theory, there is no such thing as electrostatic, right? We said that if you have a particle that is what does the meaning of an electric field? Remember, how do we measure classically? Again, we go back to classically measurement of an electric field. How do you know that the particle has an electric field? You put another test particle, or you put another particle, and you measure how this particle changes its momentum, right? Changes its trajectory. And because it's charged, and then you say, oh, then I'm assuming that it is subject to a force, and the force is derived from some potential, right? And this is the and the force gives me a field, essentially, right? This is what you say. I'm saying, look, I'm putting some charge here. But how do I know that there is a field? Know that there is an electric field? Because I'm seeing its effect on the motion of other particles. I'm putting, I have a charge here, and I put an electron here, and I'm saying that this electron starts to move in space. Right? In quantum field theory, right, the reason why this electron starts to move in space is because these guys exchange virtual photons. So there is no such thing as a field which is decoupled from the photons, right? The cumulative effect of all these photons that are being exchanged between these particles is what produces to us classically what we interpret, or people used to interpret up to 80 years ago as electric fields. But the description we currently have for that, for the same phenomena, is via these Feynman diagrams and the exchange of these virtual photons. So I'm not losing anything. I'm describing the same thing in a different way.
So a superposition of these two 4 vectors will always maintain the 0 component, the time component as 0. So how do you produce?
I have a choice. This is a choice of a gauge. I could choose other gauge. And then I would end up, it doesn't have to be 0, but I would still end up with 2 independent states. The important thing to remember, I could make different choices of gauges, right? And I could play with that, and I could get different independent vectors. It's just going to complicate my life, right? If I make this choice of gauge, then I would end up with the simplest description of a single quantum photon, and that will tell me that for a single photon I have to have these 2 polarizations. Let me finish one thing, and then I'll continue to answer this question because because we're coming to wrap up. So just one thing to finish, and then I haven't forgotten you. This polarization is not unique. Okay, I can choose circular polarization states, right? So these choices, it's just a choice of basis essentially, right? This choice is not unique, right? Often we can choose, or people choose, often one uses the circularly polarized states. Right, which denoted by epsilon mu minus or square root of 2 for normalization. This is 0, 1 minus I 0. Epsilon mu plus, which is minus 1 over square root of 2, 0, 1 I 0. Now I'm going to show you, it's not going to be today, it's likely going to be on Thursday, that these states correspond to the Z component of the spin of the photon, to be SZ. These states to plus minus 1. These states correspond to the Z component of the photon spin, the spin of the photon, to be Sz is plus minus 1. So associated with the intrinsic angular momentum. Okay, I'm not going to show it right now, but I will show it on Thursday. So I think since we haven't made enough progress, then I will just take Thursday for continuing the lecture, and then the next Tuesday we'll do the tutorial. That also means that the next problem set will be postponed. But that's okay, because then the thing we'll look at is speed. Yes, now I'm back with you for more questions. Any more questions? Well, if you don't have any more questions, then we'll just continue with the discussion of the photon spin. And then I'll introduce you something which is called helicity. And then we'll discuss some symmetries, some parity and conjunction. And then we'll extend the discussion further to massive particles. That will lead us to the Klein-Gordon equation, then for the Procca equation. So terribly difficult once you accept the formalism, but now it gets a little bit more technical, so you have to be slightly more careful on what I'm doing. All right, more questions? If not, then have a great, what happened? What happened? I don't know, this thing's very strange.
The cable connected?
Yeah, maybe, it's okay, I stopped the video. So we can just end it up. So I'm sorry for the 1 minute delay I had, because I had to reboot my computer. Of course, always at the worst possible time, but at least it was not more than that. Still recording.